Hello everyone, welcome to the Material Science class MIC 300. This is a comprehensive video on some important and practical problems that we would experience as a material engineer or a material scientist, which are relevant to the dislocations and the strengthening mechanism. So the objective of this video is just to give you some of these practical problems and then to understand how we can explain this problem and or what we should expect for this practical problem based on our discussion over the previous videos on the dislocations and the strengthening mechanism of whatever a single crystal material or polycrystalline material. So for example, this is one of the first examples or practical problem that we would experience as engineers is to understand the strengthening mechanisms of a pure aluminum. We said that aluminum is a metal, pure metal in general, they are kind of weak materials. And if you recall from our discussion chapter 7 that we said any pure material or any pure metal as it is just made by the conventional casting processing methods, it's going to have a certain dislocation density. The dislocation density is going to be like around 10 to the power 3 millimeter power to the negative 2 or millimeter to the power negative 2. But after the plastic deformation, the dislocation density inside the material microstructure is going to be multiplied. It's going to be severely and highly increased. It would reach to up to 10 to the power 10 or 10 to the power 9. It depends on how much of plastic deformation we are going to apply over the material. Even if we have applied severe plastic deformation, this is a mechanical method, and mostly what's going to happen to a material that is going to be severely plastically deformed, this material, there are lots of changes over the material microstructure because of the severe plastic deformation. So again, we said that the pure metal, before the plastic deformation, it will have a certain dislocation density. The density in that case is going to be small. It's going to be like around 10 to the power 3. But after the plastic deformation, the dislocation density is going to be severely and highly increased. Especially if we're going to do severe plastic deformation, we can achieve even under the severe plastic deformation a high dislocation density that it would reach up to 10 to the power 12 in some cases. So the increase in the dislocation, that is going to make it difficult for the material to exhibit any plastic deformation, and this what increase the dislocation multiplication. This one is going to increase the strength of the material. In addition to the increase of the strength of the material because of the dislocation multiplication, there are some other mechanisms that could exist based on what we are going to do to this material, also based on the material type. Here we are talking about pure aluminum that it will be processed by severe plastic deformation at room temperature. So there are three things here that you should identify. First, that it is pure metal. It is not alloy. Second, that it will be plastically deformed. And third, it will be plastically deformed at room temperature. So the question is, what are the different strengthening mechanisms that would exist for this type of material under these processing conditions? We are expecting for this pure aluminum that its strength is going to increase. Why? So simply in this case, we have only two strengthening mechanisms. One of them is the grain size reduction. As we explained over the previous video, we do have three mechanisms, three things that would lead to an increase in the strength of any material, especially metals. One of them is the grain size reduction. The second one is the solid solution formation, like we form a solid solution by alloying in case that we do have an alloy. But here we don't have an alloy. We are talking about pure aluminum, and the pure aluminum will be still pure aluminum as it is. It means that there is no alloying here. So the strengthening due to alloying or the strengthening due to solid solution formation is not exist in this scenario. Is not exist in this application. But the third one is the strain hardening, which is do exist. So that's why in this example, in this problem, we have only two strengthening mechanisms, two reasons that would lead to an increase in the strength of the pure aluminum after the severe plastic deformation at room temperature. If you recall that we said that the grain size reduction is one of the strengthening mechanisms, this is because of the plastic deformation is expected to decrease the grain size. As long as we are going to do severe plastic deformation, the conventional plastic deformation processing, in many of the cases, they probably gonna lead to some reduction in the grain size and the formation of new grain boundaries, but not significantly. That even the strengthening that we would achieve by the conventional plastic deformation processing through the grain size reduction, it is very, very negligible. And as long as we are doing plastic deformation at room temperature, the main strengthening mechanism that is going to come into play is the strain hardening. But if we are going to achieve severe plastic deformation, it means that the amount of this plastic strain is going to be high, very high amount of plastic strain, and definitely this would lead to a decrease in the grain size from the micro scale to approach nanoscale grain size. And this what will produce a material that is known as ultra fine grained material. So if we are going to achieve severe plastic deformation to any pure aluminum, in many of the cases the grain size will be severely and significantly decreased from micrometer scale to approach few nanometer scale or hundreds of nanometer scale, depending on how much of plastic deformation that we are going to achieve or apply to this material. Make sense? So in that case, the grain size reduction will be a big deal. It will be a very important mechanism, and the strength of the material is going to increase because of the grain size reduction. So this is one reason, one mechanism that is going to increase the strength of the material. So to answer this question, your objective is just to mention that one of these mechanisms, the grain size reduction, and this is because the severe plastic deformation is expected to decrease the grain size. Then you are going to explain why the grain size reduction it is considered as a mechanism as explained over the previous video. We said that as the grain size decreases, more grain boundaries they're gonna be generated. New grain boundaries will be generated, and we said that these grain boundaries they work as obstacles in front of the dislocation to move from one grain to the next grain. Why? Because of 2 points, because of 2 reasons that explained over the previous video. So this is for the first strengthening mechanism. The second one is the strain hardening. Strain hardening because the plastic deformation has been performed at room temperature. We define the strain hardening. This is a mechanism of strengthening the material, and this is typically existing case that we are plastically deform the material at room temperature. Strain hardening is conjugate to the multiplication of the dislocation density inside, or the dislocations. More dislocations will be formed, more kinked and overlapped dislocations will be formed up on the severe plastic deformation of the material at room temperature. And as the dislocation, so allowing for dislocation multiplication. So the strain hardening, it is conjugate all the time, related all the time to the increase in the dislocation. As I said, the pure aluminum by itself, it will have a dislocation density of around 10 to the power 3. After the severe plastic deformation, at least it's going to be 10 to the power 9. So it is severely increased, significantly increased in the dislocation. And as we discussed, these dislocations, they're going to overcome or obstacle the movement of one another. It means that they're going to be completely overlapped, making the achievement of the plastic deformation difficult, and this what increase the strength of the material as explained over the previous video. So to answer this question, you're going to say that the second strengthening mechanism is the strain hardening, and this is because the plastic deformation has been already performed at room temperature, allowing for dislocation multiplication. Then you are going to explain the strengthening through the strain hardening mechanism as we explained over the previous video. Make sense? Alright, so one another example here which is also relevant to the identifying the strengthening mechanism and explaining the strengthening mechanism that would be exist for a certain material under certain or specific processing conditions. So one material example here is aluminum alloy. And what are the strengthening mechanisms of an aluminum alloy? So here we are talking about the alloying. So probably the alloying mechanism as a strengthening mechanism would come into play, and it should be considered, or it may not. Depend on what? Depend what is your reference, which material that you refer to. If you are referring to the aluminum alloy, and we are interested in identifying what is going to happen as it changes in the strength and the microstructure of this aluminum alloy because of a certain processing condition, in that case, the alloying mechanism, it will not be considered. So again, if my reference is the aluminum alloy itself, and I am interested in investigating what's going to happen in terms of a strengthening mechanism, or it changes over the microstructure and the strength of the aluminum alloy, it means that my reference, my raw material, the raw material that I'm considering here, it is the alloy itself. It means that the alloy, it will not be counted as a change. The alloying, it will not be counted as a strengthening mechanism. But if our reference is a pure aluminum material, so the alloying process would have a contribution to the strength of the pure aluminum. Now I'm referring to another material, which is the pure aluminum. Make sense? So here we are talking about an aluminum alloy, and so far we have no clue what is our reference, which is the raw material. Here we are talking about an aluminum alloy, so this is one thing that is processed by severe plastic deformation. So we are going to achieve or apply severe plastic deformation, and we see that the severe plastic deformation is going, the first thing that the severe plastic deformation is going to achieve over the material microstructure is going to decrease the grain size. So the grain size is expected to decrease as long as we do have a severe plastic deformation. Another thing that this plastic deformation has been performed or carried out at room temperature. At room temperature, it means that there should be strain hardening. So the plastic deformation by itself is going to decrease the grain size. The plastic deformation plus it is done at room temperature, so this is gonna give another mechanism, which is the strain hardening mechanism. When it is compared to pure aluminum, so the pure aluminum, it is my reference. This is the reference. This is the raw material. I'm comparing all the changes that is going to happen to this aluminum alloy when it is compared to pure aluminum. Any alloy, when it is compared to its pure metal material, it will be more stronger because it will have a higher strength and lower ductility. What is the reason? Because of the solid solution formation, because of the alloying. As we explained that this alloying, the impurities, when we perform or form this aluminum alloy, the impurities will be receding as enters inside the material microstructure or atomic structure, or the lattices, the difference between the different lattices, as either interstitial solid solution or substitution solid solution. And this will produce some lattice strains, and this lattice strain will interact with the dislocation, and it will obstacle and impede the dislocation motion, making achieving the plastic deformation difficult. And in that case, that's why the strength of the material is going to increase, as we explained over the previous video. So the alloying is going to increase the strength. So our reference here, it is the pure aluminum. So what are the changes over the pure aluminum? As long as we do have aluminum alloy and we are going to perform a plastic deformation, severe plastic deformation, and this plastic deformation, it will be performed at room temperature. Three things. So that's why we are expecting the three strengthening mechanisms to be exist for this scenario, for this case of the material. One of them is the grain size reduction, strengthening. The second one is the strain hardening. Why? Because we are performing plastic deformation at room temperature. The third one is solid solution strengthening. Why? Because we do have an alloy. So this is a new strength that it will be included in this case when compared to the previous example. Why? The previous example we were talking about pure aluminum and there was no any alloying at all. But here there is an alloy. It means that this strengthening mechanism is going to come into play. So grain size reduction is strengthening. We said that typically the same way, because of the plastic deformation is expected to decrease the grain size. Then you are going to explain how the strength of the material is going to increase because of the grain size reduction. There are lots of grain bond that it will be formed on the reduction of the grain size, and these grain bonds, they are work as obstacle. They are impeding the dislocation inside the material microstructure, making the achievement of the slip or the microstructure slip or the plastic deformation difficult, increasing the strength of the material or indicating a high strength of the material. And why the grain boundaries are impeding the dislocation motion? There are two reasons. Because because of the random atomic structure, making difficult for the dislocation to keep on changing its orientation and its slip system as a slip plane and slip direction to go through the grain boundary. Then the second strengthening mechanism is a strain hardening strengthening, which is because the plastic deformation that has been performed at room temperature, allowing for dislocation multiplication, and at this dislocation, the dislocation density, as we mentioned, it will be highly increased, making the dislocation overlap. They form like kinks inside the material microstructure, and they're gonna impede each other. Every dislocation is gonna impede the motion of one another. Then you are just gonna explain in detail how this strengthening mechanism or the strength is going to increase because of the strain hardening. Then the third mechanism, which is the alloying, which is the solution formation or strengthening. This is because of the alloying that results in either interstitial or substitution solution. And then you're gonna explain the mechanism, as I just mentioned, that these interstitial or substitutional atoms, these impure atoms, they generate some lattice distortions around them, and this lattice distortion is going to interact with the dislocation and is going to impede the dislocation motion, indicating an increase in the material strength. Make sense? Alright, so for this second example, so over the previous example, we were discussing for two different scenarios or two different cases of the material. One was pure metal, the second one was an alloy metal. We were discussing the strengthening mechanism that would be exist depending on the processing condition, the material processing condition. So in this case here, we are interested in discussing all the changes that we should expect over the material microstructure and the material mechanical properties of a pure metal material that is processed under specific processing conditions. So again, we are interested here in explaining all the changes over the material microstructure and mechanical properties of a pure metal. So our reference is a pure metal material that is going to be processed under certain processing condition, material processing condition. Like we are going to perform some plastic deformation in a certain way under certain temperatures. So what we are expecting in terms of changes over the material microstructure and its mechanical properties. We are not interested in identifying the strengthening mechanism as much as we are interested in explaining all the changes over two things: the microstructure, what are the changes, and the mechanical properties, what is going to happen. And in order to explain the mechanical properties, the changes over the mechanical properties, your objective is just to mention whatever the strength of the material is going to increase, what's going to happen to the ductility of the material is going to increase or decrease. Just to mention these things and mention what are the reasons behind these changes over the material mechanical properties. But the tricky part here, or the new thing somehow, is the material microstructure. What's going to happen to the material microstructure? In fact, this example covers like around 4 chapters or something over that we have covered in the course so far. For example, in the first scenario that we do have a pure metal, so remember that your reference is a pure metal. So if we're going to do alloying, definitely the strength is going to increase, and the alloying strengthening mechanism is going to come into play, and it should be mentioned, should be considered. And in addition to, there are other things that is going to the other changes over the material microstructure also due to alloying, it should be mentioned. So here our reference is the pure metal material itself. So the first case that it will be considered here is the material that is plastically deformed by cold rolling. So the pure metal, which is our reference, it will be plastically deformed by cold rolling. So what is the rolling operation? Rolling operation, it is, I'm pretty sure that some of you have an idea about it, but anyway, very quick, in the rolling operation, in the conventional process, that we are using two rolls, and these two rolls are rotating in certain direction. Let's say that they are rotating in this direction. Then we are preparing the material sample. Then we prepare a material sample. This material sample, it comes in the form as slab or plate with a certain thickness, width and length. So, and then we are kind of squeezing this plate between these two rolls. These two rolls applying two high forces or high forces known as the rolling force over this plate, which will be then squeezed between the two rolls. And as long as these two rolls are rotating, so they're gonna kind of feed and gonna keep pushing this plate to be like extruded or ejected from the other side. So this is like the entrance and this is the exit of the rolling operation. So there should be something that is going to happen up on we perform this rolling operation over this material. One of the changes definitely that there should be a plastic deformation. Why? Because the thickness, for example, is going to be severely decreased. It means that we should achieve some plastic deformation over the material in order to change the thickness. And this rolling operation, it is one of the conventional metal forming process that is used in manufacturing, as used in industry. We are using this process for metal forming. So what are the changes that we expect over the material microstructure and the material mechanical properties upon we perform this rolling operation? Another thing that you should consider here is that this rolling, it will be carried out as cold rolling. Cold rolling, it means that it will be performed at room temperature, because the rolling operation, it could be done as hot rolling. It means that we have to heat the material into a certain temperature. It could be probably higher than the recrystallization temperature of the material. Then we are going to perform the rolling operation. It means that we have to put the pellet or the raw material before rolling into a furnace, and we have to heat it so much for a certain amount of time. Then we're gonna put it during, or we're gonna carry out the rolling operation. In that case, the type of the rolling operation will be hot rolling. But here we are performing rolling operation as cold rolling. Cold rolling, it means that we are not going to heat the material, but instead we are going to perform the rolling operation at room temperature. It means that, in other words, this indicates that we are going to achieve or apply a plastic deformation at room temperature over this pure metal. So the question is, under this processing condition, what's going to happen to the material microstructure as it changes? The same thing for the mechanical properties. Make sense? So the first thing, let us start with the material microstructure. And in order to understand the changes over the material microstructure, we should first understand what was the material microstructure before rolling. Then we are going to explain what's going to happen as it changes over the material microstructure after rolling. So before rolling, the material microstructure, since we are talking about pure metal that had been conventionally produced by casting, like steel making, for example, or like the iron as we extracted by nature as a raw material, as a pure metal. So in many of the cases, the microstructure before rolling is going to be uniform microstructure. What does it mean, uniform microstructure? It means that the grains, here we are talking about polycrystalline material, the grains inside the material microstructure, they are kind of similar everywhere through the entire material microstructure. This indicates a uniform material microstructure. So what does it mean, a uniform material microstructure? It means that there is similarity in the shape, in the size of the grain everywhere through the material microstructure. This indicates that we do have a uniform material microstructure. Another thing, that this uniform microstructure has grains, and these grains are equiaxed. As we said, the equiaxed Grains, these are the grains that has almost the same size, the same dimension in all the directions. It is kind of cubic. It is kind of spherical. That is fine if we can represent this grain as a sphere. And this is typically, so this is before rolling. So if we're gonna consider this figure that indicate a representation of the changes over the material microstructure, so this is the material before rolling. Before we do the rolling operation, as you can see, the grain size it is kind of big. The grains are large and they are kind of equal axis. It means that this part it is kind of all the grains having the same size. As you can see, then this is as we do the rolling operation, as we feed this material, and this is on the other side, this is after rolling. So this side there is after rolling operation. This is gonna be the shape of the grain after we perform the rolling operation. So as you can see, the grains after rolling will be kind of elongated. So before rolling, the microstructure, it is uniform microstructure with the grains are equal axis having the same direction. That is fine to represent like cube or like sphere inside the material microstructure. Even the dislocation density is usually small. As we said that pure metals before any plastic deformation, the average size of the average value of the dislocation density for this metal is going to be around 10 to the power 3 millimeter power to the negative 2, as we mentioned over the previous videos, and this is before rolling. Also, the microstructure has low angle grain boundaries. We explained that the grain boundary, it could be with a high angle grain boundary or low angle grain boundary. Low angle grain boundary, it means that the misorientations between the grain, it will be kind of small. It won't gonna be significant before rolling. Here we are talking before rolling that the grain boundary type, it will be low angle grain boundary. And these specifications of the material microstructure, if we're gonna consider from the mechanical properties perspective, it means that this material is kind of weak, and this is what we should expect about the pure metal before any processing. But after the processing, like cold rolling, after rolling, the microstructure becomes uniform. This is one of the things that we should expect, that the material microstructure becomes non-uniform. The non-uniformity that it will be achieved through the material microstructure, it comes because of so many things. One of the things that the grains will be elongated in the rolling direction. As you can see, the grains here, they were kind of equal axis, but now they are elongated in the rolling direction. They're gonna be like slabs or plates or layers, forming layers inside the material microstructure. So this will produce some non-uniformity inside the material microstructure. It's gonna make the material microstructure non-uniform from one location to another location. Another thing is that the dislocation density is going to be severely increased up on the severe plastic deformation by cold rolling, which could reach at least 10 to the power 9 to 10 to the power 10. It could be increased further as long as we are performing more rolling operation over the material. So after rolling, the dislocation density is going to increase. So all of these, remember, here we are focusing only over the changes over the material microstructure. So what will be the shape? What was the shape of the grain before rolling, and after rolling, what's going to happen? Definitely it will be elongated. What about the dislocation density? Because this is something related to the material microstructure. The dislocation density is going to increase from 10 to the power 3 to 10 to the power 9 to 10 to the power 10. Even it could be increased, as I mentioned, if we perform more rolling operation. So the dislocation is going to be keep on multiplied. Grains may be subdivided as long as, and subgrains may be formed as long as we are going to perform more rolling operation. So as you can see, these grains, think of it in this way, like these grains were after rolling, like think that you have done one pass of the rolling operation, one cycle of the rolling operation. So the grains were already elongated. How about if you are going to repeat over this rolled material? How about if you are going to repeat the process one more time? So these grains were already elongated. So if you're gonna perform the rolling operation one more time, these elongated grains may be fractured, may be broken, and in that case may be subdivided and in that case, the grains would be broken down into multiple grains, into different small grains. And this definitely will result in a severe reduction in the grain size. The grain size, as you can see, so after one cycle, for example, of the rolling operation, the grain wasn't at a certain size, but we kind of keeping and maintaining the size as it is, but instead we are elongating the material. The grain was elongated, so the volume and the size of the grain could be still the same. There is no specific reduction in the grain. But if we have performed one more cycle of the rolling, these grains, these elongated grains could be broken down, could be subdivided, and in that case, subgrains. Subgrains, it means that the fractured part or portion of the elongated grain will be separated and it will form another new grain with a smaller size. And this is going to indicate a reduction in the grain size. So grains may be subdivided and subgrains may be formed, and this is going to indicate grain size reduction. Make sense? The other option is, or the other thing, that the misorientations between the grains is going to increase. What does it mean, the misorientation? We said that the material microstructure of a polycrystalline material, it has multiple grains, and every grain has a specific crystallographic directions. The atoms are arranged in a certain manner or a certain direction over one grain, that it will be different than the next grain. The grain that is next to it. So this, if we're going to consider like two different grains, there could be some misorientation, difference in the orientation between the crystallographic orientation or direction of arrangement of the atoms of one grain with respect to the crystallographic direction of the atoms of the next grain. So this misorientation, it could be high or it could be low. If it is high, this indicates a high angle grain boundary. If it is a small misorientation, this indicates a low angle grain boundary. So before rolling, the grain boundary, it is conventionally low angle grain boundary. But after rolling the grain boundary, the misorientation is going to increase, resulting and forming high angle grain boundaries are formed, especially as long as the grains will be subdivided. If there is subdivision, if there are subgrains that is going to be formed, in many of the cases, these subgrains will be formed with high angle grain boundaries. So these are the changes over the material microstructure due to rolling. But after we perform this rolling operation at room temperature, which is called rolling, what are the changes over the material mechanical properties do we expect because of this process? So the changes over the material mechanical properties, based on these changes over the material microstructure, one of the things definitely that the yield strength and the tensile strength of the material is going to increase. Then you have to mention what are the strengthening mechanisms that is going to lead to an increase in the strength and the tensile strength of the yield strength and the tensile strength of the material. One reason or one mechanism is the dislocation multiplication because of the strain hardening or the increase in the dislocation density due to strain hardening mechanism. As we mentioned, we are performing plastic deformation at room temperature. So this would result in an increase in the dislocation density from 10 to the power 3 to 10 to the power 9 to 10 to the power 10. It means that there is a significant increase in the dislocation due to the strain hardening. So definitely the strength of the material is going to increase. Another reason of the increase of the strength is the formation of new grain boundaries due to the grain subdivision. We said that if there are subdivision, it means that there is more new grains will be formed, new subdivided grains will be formed, and these subgrains will form new boundaries. And this is which is relevant to the grain size reduction. So it is kind of a little bit different than the conventional grain size reduction, the strengthening due to grain size reduction, because as we explained, as long as the grain size is going to decrease, this will result in a formation of new grain boundaries. And these grain boundaries, they are work as obstacles in front of the dislocation to move, and this what increase the strength because of the grain size reduction. Here, it is not exactly because of the grain size reduction, but it is because of the grain subdivision. which is also indicate a grain size reduction, because the new formed subdivided grain, the subgrains, will form another grain with a smaller size. But physically, we are not decreasing the size of the grain, but we are breaking down. We are dividing the grain. We are cutting the grain into multiple subgrains. So the formation of these subgrains will form or generate new grain boundaries. And as we mentioned here, these grain boundaries are high angle grain boundaries that make it difficult more for the dislocation to leave one grain to the next grain. As we said over the previous video, that as the grain and the misorientation between the grains increases, it will lead to an increase in the strength of the material. So any material with high angle grain boundaries definitely it will be stronger than the material with low angle grain boundaries. So after rolling, the more high angle grain boundaries will be formed. This definitely is going to severely or significantly increase the strength of the material. So this is another reason why the strength is going to increase, because of the formation of new grain boundaries due to the grain subdivision. And the other thing is that the formation of the high angle grain boundaries, we probably could increase the number of the grain boundaries, but still the grain boundary as low angle grain boundary. So we are going to achieve some increase in the strength because of the increase in the number of the grain boundaries. This is one mechanism or one effect or one portion of increase. It will be contributed to the increase in the number of these grain boundaries. But another contribution that comes from being high angle grain boundary. So these are the main three reasons behind this strengthening mechanism, or could be considered a strengthening mechanism. So we do have a strain hardening, which is relevant to the dislocation multiplication, because we are performing the rolling operation at room temperature. Another mechanism that comes because of the grain size reduction or the formation of new grain boundaries, which are high angle grain boundary. So if the strength is going to increase, what is going to happen to the ductility of the material? We said that in many of the cases, as long as the strength is going to increase, the ductility somehow is going to decrease. If we are increasing the strength, the ductility is going to decrease on the other side. So the ductility will decrease mainly because of the increase of the dislocation density and the formation of new and high angle grain boundaries. So these two things are the reasons behind the increase in the strength. They are the same reason behind the decrease in the ductility. Because to have a material that is ductile, ductility, it means that the material, it can be easily plastically deformed without fraction. The ductility to be high, this requires a material that can perform plastic deformation without fraction. And the plastic deformation to be performed, as we explained in chapter 7, this requires that this material allow for the dislocation to move inside the material microstructure. So to understand whatever the material has a high ductility or low ductility, we should investigate the way by which the dislocation can be moved inside the material microstructure. Is it easy to move the dislocation inside the material microstructure? So this is going to indicate a ductile material. But if the dislocation motion, it is kind of difficult to be performed or achieved inside the material microstructure, this indicates a brittle material, or this indicates a severe decrease in the ductility. Make sense? So you could measure the increase or the decrease or the changes over the ductility by whatever it is easy or difficult to move the dislocation inside the material microstructure or not. So for this case, what should we expect? Or as it changes over the ductility, is it easy to move the dislocations inside the material microstructure or not? Definitely it is going to be difficult after rolling. Why? Because, and this indicates a decrease in the ductility. The reason is that the increase in the dislocation density. As we increase the dislocation, this makes the number of the dislocations are overcrowded inside the material microstructure, and they're going to be overlapping. There should be overlapping between the dislocation. Probably in some cases, we may have the number of the dislocations inside the material microstructure is going to increase, but they are not overlapping. So this is something that you should understand. Probably we may have a material with a high number of dislocations inside the material microstructure, but somehow they are arranged in a certain way to allow every one of these dislocations to be easy to move inside the material microstructure. So in that case, we're gonna end up with a ductile material. So the material may have a high dislocation density. In the meanwhile, it could be ductile, but this mainly depends whatever there is overlapping, that these interaction, these dislocations are interacting together, overlapping together, forming kinks, and make it difficult for one dislocation to move the other dislocation. So in that case, the ductility is going to decrease, and this is going to happen after rolling. So after rolling, we are increasing the dislocation density, yes, so that's why the strength has been increased. But in the meanwhile, and this is the problem, that these dislocations are very random, are overlapping, making difficult for the dislocation from one dislocation to move through the grain because of the overlapping. They are kinking together, everyone impede the motion of the other one. So, and the grain boundaries serve as obstacles for the grains to move or rotate, and the grain boundary to slide. So the grain motion, ductility requires the grain itself to rotate or to move. In the meanwhile, as I mentioned, so the dislocation motion, you could measure the ductility, the changes in the ductility, whatever, is it easy to move the dislocation or not. Another way of measuring the ductility, and this is what is more likely to be more accurate for the description of a ductility of the material, as even we explained this very quick before, is that the grain motion, the ductility requires the grain to rotate, to move, or even the grain boundary to slide. There should be like sliding between two different grains, or between two different grains over the grain boundary. This is known as grain boundary sliding. So these changes, whatever, if the grain, it is easy for it to move or to rotate, or the grain boundary to slide inside the material microstructure, this definitely indicates a more ductile material. But because of these dislocations, which they are very high number of dislocations, and the meanwhile they are overlapping, and the grain boundaries, which are high angle grain boundaries, they are work as impedances or obstacles in front of the grain to move or to rotate, or even the grain boundary to slide, and even it is not easy to move the dislocation from one grain to the other grain, and this what result in a severe decrease in the ductility of the material. Another reason is that the material dislocation approaches the saturation after the plastic deformation, which makes the material can exhibit small plastic strain. So what does it mean, this last statement? For example, before rolling, as we mentioned, the dislocation density was 10 to the power 3. After rolling, it has been increased. It has been severely increased. How about if I decided to, for example, in this case, after one cycle of the rolling operation, it has been increased to 10 to the power 9. Then after the second cycle, if I decided to do one more cycle of rolling over this rolled material, one more cycle, so this is going to give us like another increase up to 10 to the power 11. After the third cycle, the dislocation is going to increase up to 10 to the power 12. Then if I gonna keep on doing the rolling operation, I won't gonna observe any changes over the dislocation density. I'm gonna almost end up with the same value of the dislocation for any further rolling process. So what does it mean this? It means that after 3 cycles of rolling, we have reached to a saturation of the dislocation inside the material microstructure. The material cannot form any new dislocations, or there is no new dislocation that can be formed inside the material microstructure. Why? We reach the saturation state. There is no ability for the material to increase or to multiply or to generate new dislocations. This also is an indication that the material becomes more brittle. That this also indicates that there is no possibility to form new dislocation. This indicates that the ductility, it has been severely decreased. Make sense? So, and this is what does it mean, this statement. So the material dislocation approaches. So after rolling, we are approaching, as you can see, we increased after one cycle from 10 to the power 3 to 10 to the power 9. After just one cycle of rolling, But after the second cycle, we could reach up to 10 to the power 11, for example. So we jump 2 orders. Then after the third one, we jump to 10 to the power 12. It is only 1 order. Then beyond the 3 cycles, as you're going to keep on doing the cycle, you're going to end up almost with the same number of, or the same value for the dislocation density. It's going to be the same. It could be increased like from 1 to the power times 10 to the power 12 to 2 to times 10 to the power 12, and so on. But anyway, it will not be going to consider as increase in the dislocation, as when it is compared after the first cycle. After this first cycle, we increase like around 6 orders. After the second cycle, we increase 2 orders. After the third, we increase 1 order. Then we reach the saturation. So after only 1 cycle, or after the rolling operation, we are approaching, or even we could achieve or reach to the saturation state of the material that gives the material in this ability to form any new dislocations. So the material dislocation approaches the saturation after the plastic deformation or after the rolling operation, which makes the material can exhibit small plastic strain. And as we define the ductility, it means that a ductile material is the one that can plastically deform without fracture. So there is no ability. It became very crowded. We reached the saturation case. There is no ability for the material to exhibit any plastic deformation because we reached the saturation state. Because as we explained, as long as, and here we are performing the plastic deformation at room temperature. So it means that there should be strain hardening. And we said that the strain hardening, it is related to an increase in the dislocation density. So if you are going to perform one more rolling cycle, we as plastic deformation, we should expect an increase in the dislocation. But now there is no ability for the material to increase the dislocation. So we reached the saturation already. So there is no further plastic deformation that we can perform over this material. And if we try to do so, the material will be fractured. It means that this indicates that the material will be converted and it's going to behave like a glass. We said that the glass, if you have a piece of glass and you try to bend it or to try to do plastic deformation to the piece of glass, it will be fractured, indicating that it is a very, very brittle material. This is going to happen in this metal after the rolling operation, and once we reach the saturation state of the dislocation density, there is no further ability for the material to perform any plastic deformation, indicating that we end up with a glass material. We end up with a very, very brittle material, indicating a severe decrease in the material ductility. So these are the changes over the material microstructure and the material mechanical properties after rolling. Make sense? Alright, so one more example. So it is also required again to discuss all the changes over the material microstructure and the mechanical properties of pure metal. So the pure metal, this is our reference material when it is processed under each one of these following conditions of processing conditions. So this condition that the material will be processed by alloying. It means that we're just gonna make or convert this pure metal into alloy. So alloying, we said that this is going to increase the strength and enhance some of the mechanical properties of the material like the strength, but on the other side is going to affect the ductility as we explained. So this is a very straightforward thing, because the thing that we are expecting in terms of changes over the material microstructure is that the formation of either interstitial solid solution or substitution solid solution upon the alloying process. So after alloying, the material forms either an interstitial solid solution or a substitution solid solution, and these solid solutions, these perform imperfections or defects inside the crystal structure of the material microstructure. So these will produce some lattice strain which are located inside the crystal. Here we are talking about a single grain or one crystal or one grain inside the material microstructure. Here we are going to discuss the changes over the material microstructure over the grain boundary, because the alloying, we are expecting that is going to affect the crystal structure, but it won't gonna say there is no significant changes that we should expect over the granular structure of the material. Granular structure, it means that The discussion about the grain boundary, the number of the grain boundary is going to increase or not, we have no clue. It could be different from one alloying process to the other one, but in the many of the cases, the changes due to alloying will be lattice changes. Lattice, it means that are related to the lattice, to the crystal structure of one single grain or one single crystal inside the material microstructure. So one of the things that we should expect upon alloying is the formation of either interstitial solid solution or a substitution solid solution. And as we explained in chapter 4, interstitial solid solution, this is the one that the host atom or the impurity atom will be receding in the gaps between the different lattice sites or between the atoms of the host material or the host pure metal alloy. The substitution, it means that the impurity atom will substitute the host material. The impurity atom that go into the solid solution impose some lattice strains which should be local around these interstitials or substitutional atoms or these impurity atoms on the surrounding host material. The lattice field or the lattice strain will interact with the dislocations, resulting in an impedance of the dislocation motion, or somehow the dislocation motion will be restricted, as we explained over the previous video. So your objective actually just to explain, we here, as you can see, we kind of are explaining the strengthening mechanism due to the alloying, because the changes, these 3 points indicate or explain what are the changes over the material microstructure. That there should be, we're going to end up with either an interstitial solid solution or substituted solid solution, and these impurity atoms will produce some lattice strain inside the material microstructure. In addition, this lattice strain will somehow interact with the dislocation, resulting in an impedance of dislocation motion. But what are the changes over the material mechanical properties? As the concentration, as we mentioned over the previous video, as the concentration of these impurity atoms increases inside the material microstructure, the tensile strength, the yield strength of the material is going to increase, and the ductility on the other side, it will be decreasing. Right, as shown here, the ductility is going to decrease. So this is the percent of elongation as indication of the ductility, while the tensile strength and the yield strength of the material, both they are going to increase. Make sense? So these are the changes over the mechanical properties and the microstructure of the material up on alloy. Make sense? So over these two examples or these two cases of the material, in one case that we explained the microstructure and the mechanical properties, it changes over the pure metal, which is our reference in case that it has been performed plastically deformed by cold rolling. The other scenario that it has been processed by alloying. How about if we do have the two processing conditions, like if we are going to process the pure metal by alloying first, followed by plastic deformation by cold rolling. It means that we are going to do the alloying first, then we are going to perform plastic deformation over this alloy metal material. Like we are going to do the alloying process followed by the plastic deformation by cold rolling. So definitely our response to this, to explain the changes over the material microstructure and mechanical properties, your objective is just to combine these two discussions. First, you're gonna explain what are the changes over the material microstructure in terms of this interstitial solid solution, the impurity and the lattice strain that is going to form, and how it interact with the dislocation, and they are impeding the dislocations. Then what are the changes over the tensile strength, yield strength, and ductility? Typically the same, just explain this portion. These are the changes over the alloying. So you're just gonna mention up all alloying of the metal, of the pure metal, these are the changes over the material microstructure and mechanical properties. Then you are going to explain again the changes over the mechanical properties and the microstructure of the alloy material because of the rolling process. Because of the rolling process, you're just gonna mention what was the material microstructure before rolling, after rolling what's going to happen, also what are the changes over the material mechanical properties which are relevant to the strain hardening and the generation of new grain boundaries, which with high angle grain boundaries. So these are the reasons behind the strengthening, and the same reasons are the thing that behind the decrease in the ductility of the material by cold rolling. Make sense? So your objective is just to combine the two discussions in order to explain what are the changes over the material microstructure and mechanical properties of pure metal up on alloying and plastic deformation by cold rolling. Make sense? Another example here, or another processing condition, that what are the changes over the material microstructure and mechanical properties of pure metal that is plastically deformed by cold rolling, and then it is annealed. So we are going to carry out the cold rolling process first, then after that we are going to do annealing. We said that annealing, it means that you are going to do heat treatment in the material, for the material at certain temperature, then you are going to cool it down with a certain rate. So this process is known as a heat treatment process, and we said that the heat treatment process over the previous video, we said that it would lead to some recovery or recrystallization or grain growth depending on the processing condition, depending on the annealing or the heat treatment process. So here it is not mentioned what is the specific temperature at which we are going to heat this pure metal. Also the time that is needed or used for the heat treatment or the annealing process. So because this requires time and amount of temperature. So at which temperature you are going to heat the material, for how long, and how you are going to cool down the material to the room temperature one more time. So these things give different heat treatment procedures and it changes over the material mechanical properties. So we have no clue what are the specification of this annealing or this heat treatment process. So we are just gonna give a discussion in general about the expected changes over the material microstructure and mechanical properties because of the annealing. But remember that our reference still is the pure metal, and we are going to do cold rolling by plastic deformation, cold rolling of the material. So we should explain the changes over the material microstructure and mechanical properties like you have done cold rolling as we explained before. So these are the changes over the material microstructure, or these are the specification of the material microstructure before rolling as we explained. Then after rolling, these are the changes over the material microstructure just after rolling. Forget about the annealing. Just answer the first part. Then you just gonna explain the materials microstructure, after annealing. So you have the option either to explain the material microstructure up on cold rolling, and then you are going to explain the mechanical property, the changes over the mechanical properties of the material up on cold rolling. So you're going to explain these changes. All right. Then you can go ahead and start to explain the changes over the material microstructure and mechanical properties due to annealing. So the new thing here, what should we expect as it changes over the material microstructure and mechanical properties because of the annealing of a material that was already cold rolled? So let us focus first over the changes over the material microstructure. So after rolling, the material, as we said, the microstructure will be non-uniform. The grains will be elongated. Sub-grains could be formed because of subdivision of the grains. The dislocation density will be high. It will be up to 10 to the power 10. In some cases, even it could be increased, as we mentioned. Also, we're going to end up with high angle grain boundaries. More grain boundaries will be formed, and it will be high angle grain boundaries. So these are the changes over the material microstructure after cold rolling. So I showed the material microstructure. I explained the material microstructure before rolling, which the reference material, the pure metal. Then after rolling, so the question is, after annealing, after rolling, which comes after rolling, what are the changes do we expect over the material microstructure? So after annealing, if the material annealing allows for recovery, recrystallization, and grain growth, the microstructure becomes uniform with grains are equiaxed. As we mentioned, after rolling, because of the rolling, the microstructure in general is non-uniform. The grains are elongated. But after the annealing of the rolled metal, the grains the microstructure will recover back again, because we said that in the recrystallization, we are recovering the original state before the plastic deformation. So we are recovering the microstructure before rolling already by the annealing process. So after annealing, and as long as it allows for recovery for recrystallization and green growth. So we are expecting that the microstructure becomes uniform one more time, and the grains will be equal axed. Then instead of having the grains as elongated grains, it will be equal axed in that case. Make sense? So this is an expected change over the material microstructure. Another expected change is during recovery. If there is a recovery, we said that the dislocation density and the lattice strain will be decreasing. We said that the key idea of the recovery, there should be a reduction, but it is a very slight reduction in the dislocation density because of the recovery. And in the meanwhile, the lattice strain is going to decrease. We said that the objective of this annealing or heat treatment process is to get rid of any embedded residual stresses inside the material microstructure. And these residual stresses are mainly generated because of lattice strain or lattice distortion that already formed because of these different imperfections up on the plastic deformation by cold rolling. So after we do the annealing, we are expecting a slight decrease in the dislocation density and a slight decrease in the lattice strain because of the recovery mechanism. But if the heat treatment process or the annealing process allow for the recrystallization, a new set of strain-free and equal axed grains that have low dislocation densities will be formed. And this is what we mentioned over the previous video regarding recrystallization. It means that we heat the material at a temperature higher than the recrystallization temperature of the material that allow for the regeneration of new and fresh crystals and grains inside the material microstructure, which will be reset back to its original state before the rolling process. So we're going to end up with grains that free of any lattice strain, that are equal axed grain and having all the same dimensions in all directions that could be represented as a sphere or a cube inside the material microstructure, and we're going to end up with a uniform material microstructure. Also, something that we could expect due to the grain growth, as long as the process allow for the grain growth, so the boundary between the annealed grains will migrate and large grains are formed. We said that there should be like grain migration, and in that case, we are going to increase the grain size. Because of the rolling process, we end up with some grain subdivision. So see, these subdivided and subgrains will be collected somehow because the grains will be migrating, allowing for merging multiple grains together to end up at the end with large grain size, and this will result in an increase in the average grain size of the material microstructure. So these are the expected changes over the material microstructure of the cold rolled material up on annealing. But how about the changes over the mechanical properties? After the rolling process, we said that the yield strengths, the tensile strengths, both they are going to increase. But on the other side, the ductility is going to decrease, as we explained. But what are the changes over the mechanical properties up on annealing? Up on annealing, the yield strengths, the tensile strengths, they are expected to decrease one more time back, especially if we're going to allow for recrystallization and grain growth, especially recrystallization due to annealing. On the other hand, the ductility is going to decrease. So we, as you can see, we are recovering back all the states of the material, all the properties of the material before rolling one more time. So the annealing is going to work against the rolling. But in some cases, and this is another thing that you should understand, in some cases we can perform the rolling operation with a very high plastic deformation strain or plastic strain, which is known as severe plastic deformation. So we are going to increase the dislocation density significantly. We are going to do abrupt changes inside the material microstructure. So even if we did annealing, we will not be able to fully recover the material to its original state before rolling. But definitely there should be some changes due to the annealing over the severely plastically deformed material, following the same trend, following the same things that we explained here, or as it changes over the material microstructure due to recovery, recrystallization, grain growth. So we are expecting a more uniform microstructure. We are expecting that the grains will not be elongated that much. It could be elongated still after annealing, as in case that we have achieved severe plastic rolling over the material, but at least the elongation in the material will be kind of, or on the grain, will be decreasing, and we could approach somehow to have an equiaxed grains in that case. Also, the dislocation density will be decreased, but definitely it will not be decreased that much to reset back to the original dislocation density as 10 to the power 3 for the pure metal material. Make sense? It means that we can, after annealing, we can relieve some of the stresses, we can decrease the dislocation, we can somehow recover the material to the original state, but not fully in case that we are applying severe plastic deformation over the material. So as this figure has been explained over the previous video, so your objective is just to indicate what are the changes. As we mentioned, during the recovery, we have a slight decrease in the tensile strength of the material, but the ductility, also the ductility will be slightly increased, but most of the decrease in the tensile strength and the ductility increase will be within the recrystallization region. Then the grain growth allows for the uniformity of the material microstructure. So these are the changes over the material microstructure and mechanical properties that we expect up on the cold rolling and the annealing. So you're going to explain what is going to happen after cold rolling, then you are going to explain after the annealing what are the changes over the cold rolled material. Make sense? Alright, so that's it for this video, for this part, and we are going to discuss this comprehensive discussion about the microstructure and the mechanical properties of this material under these different material conditions, processing conditions, and we are going to consider more other important cases, but over another video. So there is, for this discussion, it will be like over 2 parts. This is the first part, and there should be another part for this comprehensive discussion. All right, so that's it for today, and thank you, and see you in the next video.